Okay, so we'll do my favorite exercise just to see if everybody is back. Just write in the chat if you're here, so we can get started. Perfect. It's good. Perfect.
Present.
That's good. Next time I'll ask the ones who are not there to say they're here, to make a sound. Very good. Curtis, are you there as well? Maybe he wrote there. It's okay. Yeah, we can get started.
I'm here. Do I have to do the exercise?
Yeah. Yeah, perfect. Yeah, you have to do the I'm joking. This just to wrap up this brief section, but I think is an important part, which is how we correctly will back calculate molecular weight C7 plus and specific gravity C7 plus with this particular formula here in the PBT reports, because that's typically not done for us. And as we mentioned, the reported molecular weight C7 plus and specific gravity C7 plus, they're just calculated based on these, arbitrary values, sometimes from Caspers of body and maybe also sometimes from this Whitson table we looked at the first day. So the exercise 10 that we'll just do together now real quick is to show the difference for the two PBT reports we have attached in this course between the calculated, direct calculated way using the Caspers of body numbers and actually back calculating based on the measured values. So everybody should have gotten this Excel sheet with molecular weight C7 plus and specific gravity C7 plus. There are for each sample, there will be 4 values or 2 values to calculate. This is what we see on the top here is the so-called wrong or not recommended ways of calculating it. And that's just straightforward using the formula right here. So we use weight percent and not mole percent because that's what's measured in the stock tank oils. And if I remember this correctly, it's the sum of the weight percentage higher than C7. We'll start with the that shouldn't matter. Divided by the sum product of the weight percentage right here, and then 1 divided by the molecular weights, which is what we calculate first. I think that should be correct. 264. Hope that's correct for the people has the report. We can double check it maybe. So in the report,
You don't have it.
huh?
You don't have it.
No, it's not provided.
No.
No. Okay, so that's not in the report. That's good. And we do the same. We use the formula to the right here to do the same way. So this is again the wrong way of calculating. So maybe not the best thing to do for education purposes to teach you how to do it the wrong way, but that's the way people are doing it at least. So again, we take the weight percentage heavier than C7. And we again use the sum product function of the weight percentage and then 1 divided by the specific gravities. And you can do this for both the oil and you can do the same for the gas condensate and you will get these values right here. But we'll try to emphasize the focus on the correct ways of calculating this. Or actually here, this is the total. No, okay, yeah, very good. And then we'll focus more on the back calculated way of obtaining these C7 plus molecular weight and specific gravity values using this formula right here, which is in the formula sheet on page 3 or 4, and also in the slide deck that we just went through. And we can start with the C7 plus molecular weight. And we start with the oil. And then we divide by the measured molecular weight, or 100%. So this is just the total sum of the entire sample. So that's actually this number right here. And then we divide by the measured molecular weight. And then we do the sum product of everything. Up until this point. Then 1 divided by molecular weight. Yeah. 261 is what we get, and it's actually the exact same formula, or the function is the same. We just have to change the molecular weights with the specific gravities, I think. Yeah, and we get 0.849 as the back calculated values. And we can first of all compare the difference. So the molecular weight of C7 plus here is 261 versus the calculated with Catsper's body 264. And we also see the difference when it comes to the specific gravities right here. And in the lab reports, depending on what field you're working at, it can be smaller or most times larger differences than what we see right here.
And like one reason why you see small difference here is because like we went through this Watson characterization factor value, and we saw that it's very close to what generally is expected for the Kac-Perez-Abadi fluids, the fluid system they use for the measuring of these molecular weights, very paraffinic. So that's why for this fluid system, maybe this Kac-Perez-Abadi molecular weight and specific gravity are reasonable compared to many other fluid systems you have in the world. But we will see tomorrow how we can develop this individual component molecular weights and specific gravity correlation as part of US model development. That will be a main exercise tomorrow.
Very good. So again, I just did it quickly. It's the same formula I just applied for this fluid, which is the gas condensate fluid, and we get these numbers. And just again, comparing them, they're not the same. That's the first time thing we see, both for the molecular weight C7 plus and the specific gravity. And as Bilal said, the reasons why they're similar is because they're more close to the general Kac-Perez-Abadi in this case, which sometimes is just arbitrary, and sometimes it can be very, very large differences as well between the two. And we'll emphasize the importance of developing this relationship and plotting these points and actually back calculating them more tomorrow. But before we leave this topic, if there's any questions, or while we're people are thinking about some questions there, unless Curtis has actually done the donut field story, it would be great just for an example there, Curtis, to emphasize the importance of developing this relationship and calculating these values for a particular field for EOS fluid characterization purposes. Would you like to share a few words from that?
Yeah, this was probably the most extreme case where getting the characterization of the oil expressed in terms of the Watson characterization factor correct had a huge impact on his study. So I can tell you a little bit the story. This is probably 20, maybe 25 years back, and it was in Dubai. There's Phillips was operating a field that I call it the donut field. It was kind of shaped, had kind of unusual round shape and a depression in the middle, and they were doing gas injection and had phenomenal amount of new PVT data. And for gas injection together with depletion, it was a volatile oil. And so they were going to do this gas EOR study. And there was a relatively young engineer. He had kind of self-taught himself the A's, all the methods of doing an EOS model characterization. He was using the software PVTX, which Philips leased back then. And maybe he'd gone to one of my courses, I don't remember, I don't think so, but he had learned the software and he had all this data, he was responsible, and he developed this equation of state that really did a great job of fitting the vast majority of data, including the more complicated PVT data, the gas injection. And so I was in the area and he asked me to drop by for a day to look at what he'd done and to discuss it. So before lunch, we kind of went through the data and we looked at the equation of state predictions. Everything looked great. And then he showed me the tuning parameters of how much he had changed the critical properties of the C7 plus components, TC, PC, acentric factor. I don't remember the exact parameters that he changed, but it was basically the properties of the C7 plus fractions, maybe some BIPs. And I started looking at the amount of correction he had to these properties, and they were like just huge. I mean, 20, 30, maybe 40% change. And it was curious, and it was just before lunch, and I said, well, I'd like to kind of look through it through lunch and try to understand why you were having to change the parameters so much to get this match. And so went through the day, looked at some of the data, and came back during the lunch break. And basically, the first thing I did was calculate this Watson characterization factor just for orientation on one sample, and then the second and the third sample, and it was like 10.2. It was in the low 10s. I don't know if I'd ever seen something that low, which meant that it was a very aromatic oil. But for some reason, he had gone in with the base characterization, assuming Katsura-Zavadi. In fact, I think what he had done, he'd literally put in all the properties from Katsura-Zavadi as the starting point for calculating critical properties and so forth. Table 5.2 in the monograph, if you want to look at that. Basically, he took those as starting point properties. But that's, as we saw a couple of days ago, that's basically the Watson characterization factor for all those single carbon numbers around 12, 11.8, 12. And even though it was the average C7 plus molecular weight gravity that gave this low 10 Watson characterization factor, very aromatic oil. But basically through all this regression, he'd been able to tweak all of the TC-PCA centrifuge, all these properties into aromatic-like properties. And so when he came back from lunch and I said, well, I think I understand why you had to change the properties so much. And I just showed him the Watson characterization factor calculations and so forth. And I said, well, let's just do an experiment real quick. And let's just use the default software characterization that will fill in the TC, PC, and acentric factor based on the specific gravity molecular weight single carbon number relationship. And by default, PVTX what it would do is that it would find that curve that we looked at yesterday that gave an exact fit of the measured C7 plus gravity molecular weight. So he put the samples in and he basically turned on this characterization factor, which filled in all the properties by default, and did the calculations, had all the data already input, all the experiments and everything. He just did kind of a prediction run, and without any tuning. And it wasn't better than his, but it was basically on top. The predictions were very close to being on top of his. And I think he had used a year of work developing this EOS model with the tuning, the regression, and everything. and making all these major changes. And I wasn't sure if he was going to go him, or he was kind of like, in one way, depressed, because that one, I don't know, issue had basically starting with the cat spheres of body, assuming that you had this vanilla envelope fluid, was so wrong. And had he used a more aromatic set of properties, he would have gotten this prediction that required very little tuning to get the final EUS. Anyway, it's a true story, and it's kind of a most extreme case of where. So I think what I want to bring as a what's the conclusion of the story here for this course and where we're at in the course is that the predictive EOS, what you basically start with as before you start doing any regression, it better be giving you reasonably accurate predictions for pretty much all the data. Maybe it won't be predicting the critical points of, swelling test data. Maybe if it's near critical samples, it'll predict a bubble point instead of a dew point on some of the samples. But the overall prediction should be pretty much reasonable, okay? And if they're not, that's a huge red flag. And with pretty much any of these software programs, the default characterization should get you ballpark predictions, with the exception of these more complex, near critical phase behavior, from the get-go. And if it doesn't, it's kind of a red flag. And about the only reason that it wouldn't do it is that you've got this wrong starting gravity molecular weight relationship that's saying it's too paraffinic or too aromatic. And if you get that, if you adjust that and go through the methods to get that right, then get some predictions that are very ballpark good starting point. The whole experience of regression and tuning will be a much more simpler, and it may not be simple, but it'll be easier and more successful. That's the end of the story. I think that's the carryover. So it's
very good.
I would just add some comments here on what Curtis said. So whatever Curtis said, like developing this molecular weight specific gravity correlation for developing US model, that's very important, and that's we are gonna see tomorrow when we will be doing or developing our equation of state model for this fluid system. But what Curtis has said, that if we do like proper C7 plus characterization and develop an equation of state model, and that the US model without any tuning, that initial US model should give us reasonable predictions. And how we can make sure that we have done proper C7 plus characterization, we will also see that tomorrow when we will be doing the exercise. But that's like we went through all the lab experiment QC, the different methods. But when we develop the equation of state models, this initial EOS model with proper C7 plus characterization work, we also use it as a guidance to see how good the quality of PBT data is. So maybe you have done the right C7 plus characterization and you have developed a good initial EOS model, but that EOS model may not be giving you very accurate predictions of the PBT data. And in that case, you may have quality issues with the lab PBT data, because there are always some tricks that you can do to close the material balances that we had been seeing before. And you may, like on the material balance, all the data look very nice, but when you start doing the prediction with that initial EOS model, you may see that some of the data or some of the PBT samples, they may not be falling in line with your equation of state model predictions. And there you can start highlighting, okay, what are the quality issues and which part of the particular experiment, which PBT data of a particular experiment is questionable from the lab.
Very good. So remember that always to back calculate based on measured molecular weights and specific gravities, such that we capture that potential change that Curtis talked about potentially in more paraffinic fluid to something that potentially can be very aromatic in this case, or something slightly less dramatic as well. Very good. There was a question here. Would we be talking at some point about merging measurements from GC and boiling point or true boiling point distillation data, i.e. using lighter fraction from GC and heavier for TBP tests, if we have a spreadsheet that could share so this is understood? So that's a good question. So in the studies essentially where you have both the GC data and boiling point distillation data available, how are we using that in practice, and how would you use this into, for instance, developing a C7 plus specific gravity molecular weight relationship? Curtis, you want to answer that quickly?
I think Bilal can probably comment on that. I can add some.
So actually, there is not a straightforward answer to this question, because there are different tools and techniques how you can integrate the TBP data and the GC data together for C7 plus characterization, and like the tools and techniques that we generally use for this kind of analysis, that's something we are going to discuss tomorrow when we will be developing the field-wide equation of state model. For this particular course, we are not going to use any TBP data for the EOS model development, but the tools and techniques that we are going to discuss tomorrow, that can easily be used if you have TBP data together with the GC data. And I think this like very specific answers to this question, I think those will be more relevant for tomorrow's session, and we will discuss these things.
Very good. So we'll continue on that tomorrow. Very good. Gerardo? Gerardo?
Yes, microphone off. Yeah. We normally work with a lab that is giving us the C7 plus molecular weight. In that case, you will be using that, right? You will be using the measured one and not the back calculated one that you just mentioned. Is that correct?
So yeah, you'll never measure only the molecular weight of the C7 plus molecular weight. The thing that you'll measure is the total stock tank oil molecular weight number, and then if there's any property provided by the lab on C7 plus molecular weight for that stock tank oil, that's, I think, almost now a standard most places that's a calculated number, and you should not use that number that they're giving, because that's based on cat sphere as a body. You should use the number that you back calculate from the measured value. And sometimes this measured value is not provided by the lab, so then you need to call up the lab and make sure that they report that in the report, because that's a very, very important number.
Yeah, but so sorry to insist on this, but I remember specifically asking the Stratum lab, right, if they have the molecular weight C7 plus is measured, and they reply, yes, it's the C7 plus molecular weight is measured with the freezing point depression way.
Yeah, so Gerardo, I think you are talking about the study we were doing together.
Yes.
Yeah. So yeah, I think there was a misunderstanding like on the lab side, because when I think it was Mo was doing the study, and when he asked them, like, did you measure the C7 plus molecular weight? They said yes, and then when he insisted on this question, and he said, did you measure the C7 plus molecular weight or the average flash load molecular weight? And then they said, okay, yes, we measured the average flash load molecular weight and not the C7 plus.
Okay, so it was a wrong communication from Stratum. Yeah. Okay, thanks. That's clear now. Thank you.
Very good. Any other comments? Hans Christian, I saw you had your mic.
Yeah, but they said that what I was thinking about, they measure the average, and then they calculate the C7 plus based on the composition, normally they using what they call the PNA, because I was working at Stratum Lab, RES Lab 10 years ago. And then we're using the PNA distribution. It means that you calculated the C6, C7, C8, and C9 molecular weight based on the composition.
Yeah.
So that is more accurate than cut sphere's body, and that you're using that values to calculate the C7 plus. So that is normally a little bit more accurate than C7 plus that you get if you're using cut sphere's body as the pseudo component.
Yeah. Very good. Yeah. End of story on that is that number is very important, and you should make sure that you get the true, at least the number that you're using in analysis should be based on actual measurements from the field that you're working on, and not some random correlation as, for instance, cat spheres of body or something else. Very good. So we're going to use this learning now into talking about molar distribution models, and what we're going to discuss now. I'm going to do a short introduction of the topic, and then we're going to cover two different models: the discrete exponential model and the gamma continuous model. And we'll see that actually this model right here, the exponential model, is just a simplified version of the gamma model, where alpha is equal to 1, a little bit high level. Okay, and the first thing we would like to answer is, why are we actually doing, why do we actually need gamma distribution models? And why are we in the first place doing heptanes plus characterization, this is all kind of related to. So the first thing to note there is that it's impossible with chemical separation techniques to identify the C7 plus components individually. And even if they were identified, it would not be actually possible to measure the critical properties and other EOS parameters for the fluids with that's heavier than C 20 plus or something around that number. And this problem is solved practically by making approximate characterization of the heavier compounds with experimental and mathematical methods. Yeah, the give control.
Yeah, this part.
Yeah.
I think just click somewhere.
No, there we go. Thanks. Sorry about that. And we understand the reasoning behind that. If we, for instance, look at C14, what's reported in the laboratory as a nice, clean, single carbon number C14 can actually consist of up to close to 1900 different isomers. So what we're actually trying to capture for a particular field is kind of the average C14 component. And when we are actually doing heptanes plus characterization, which is after we've done all the QC work that we've been talking about so far, we jump into this heptanes plus characterization, which is a very, very important step before we do EOS predictions and tuning of the equation of state. So the approximate procedure can be split into 3 main tasks, where the first one is dividing the C7 plus component into a number of fractions with known molar compositions. That's where we are going to talk mainly about the gamma distribution model. And then we will, as we will also talk about here, when we've been talking about that a little bit already, is to define a relationship between molecular weight, specific gravity, and boiling point of each fraction. So this is actually exactly what can be measured in a TBP experiment, so an ASTM distillation type experiment. And also this plot that we just talked about is related to number 2. And then the last point is actually estimating the critical properties based on a wide range of different correlations. These critical properties such as TC, PC, eccentric factor, volume shifts, and BIPs, which we at this point we don't know, or we assume that we don't know what these properties are and mean, but that's the topic of the next section, so we'll get to that. And when we are talking about modeling of C7 plus distributions, we are mainly internally developed or using a gamma model, which is the most generic model for these purposes. And I remember back in the days a few years ago, I asked Curtis of all the papers that he wrote, which paper was or was he the most kind of satisfied with. And this paper, by, I think from 83 or 84 on C7 plus, modeling C7 plus distributions. Can't remember exactly the name, but the about the gamma modeling approach was, at least at that point, the one that he pointed out as being the most time appropriate and I guess also widely adopted by the industry. Any comments on that, Curtis?
Yeah, favorite. Yeah, 1980 was actually when it was presented. We got it in the journal. It took 3 years in 1983, and yeah, I mean it was timely because the laboratories only gave C7 plus properties and amount. So between then and now, when you get 40, 50 components. And then when you got always the same 11 components with no resolution on this very important heavy C7 plus, I think that's probably why it was so timely. So,
very good point.
And we can upload the paper and that's happening plus characterization.
I think it's already uploaded there. 83 paper from Curtis, and Bill will go through this in detail in a little bit, but. And this is a figure from the SB monograph that is also uploaded in the course material, just showing a few different versions of the gamma model or with different shapes essentially, and also and the model is from a high level perspective requires 3 input parameters: an average molecular weight of C7 plus, which typically is sample specific, a bound, a lower bound, and a shape. And when we do, like, let's say we create equations of state for, the Bakken or Vaca Muerta or Permian or a big field like that, we usually try to find field specific shapes and bounds. So they are, call it constant, these parameters for a particular field, while the C7 plus is sample dependent. So if you're talking about a gas condensate fluid, that will have a much lower molecular weight of the C7 plus and a higher API, versus a black oil, maybe even from the same field, that would have a much higher molecular weight of C7 plus and lower API. So this is sample specific. But when you hear about the gamma model, just think that these 3 parameters is required here. And here we just see an example of a molecular weight C7 plus of 200. Or an average molecular weight and the bound of 90, showing a shape of 0.5, a shape of 1, which is this one special case of the gamma model, which is essentially the exponential model, and then an alpha equal to 2, which, for instance, could be a biodegraded oil, I guess. So having like a hump like this. So this could be biodegraded oil, not very pretty. We can mention that for those of you who are working on conventionals, we have found there to be, typically alphas, depending on what field you're in, maybe between 0.55 to 0.7. The straight line here is what's default and the only option you can use in, for instance, PVT sim. So that's the exponential model that we'll talk about in a little bit. And the ranges for alpha is typically between 0.5 to 2.5. And as I just mentioned, the alpha equal to 1 is the exponential distribution, which is what is recommended in general if no GC or TBP data is available. The bound that I just introduced can be physically be thought about as the minimum molecular weight that can be found in the distilled fraction of C7 plus, and that number is typically 90 or close to 90 in general. Okay, so on that note, I'll just give the word to Bilal.
Okay, so now actually we will go through in more detail about the different model distribution models that that Matthias briefly mentioned. But before that, we just tried to go through why we are talking about model distribution models. And as Curtis said that in 1983, like PVT Labs, that they used to measure like C7 plus as one component, and then there was no essentially no resolution on the heavier ends of the C7 plus fractions. And there it was very at that time the model distribution models was a big deal, and it was really needed for proper equation of state model development, because you needed more information on the C7 plus fraction. So the first, that model distribution models, what do? They actually describe the distribution of the amounts of Cn plus fractions, and Cn plus could be a C7 plus or C10 plus or C11 plus, depending on what kind of GC data you have. So normally now, if you have in the GC data, we have like these isomers for these lighter fractions. We saw before, like for C7, you have benzene, toluene for C8. So when these isomers are reported, then generally your Cn plus is the C10 plus or C11 plus. The carbon number from where the single carbon numbers are actually start in your GC data. In the absence of extended GC data, so that was the case in 1980s, when there was no extended GC data available, and we only had this Cn plus as C7 plus. We didn't have any more resolution on the heavier ends. In that case, you needed some kind of model to give you the model distribution of C7 and heavier fractions into the equation of state model, where your heaviest component could be C36 plus or C30 plus, etc. So at that time, when we didn't have the extended GC data, this was the real use of the model distribution model. But now, when we look at the PVT reports and we get the GC analysis, we get the extended GC data usually, and we get the data until C30 plus or C36 plus, and we know that even though that data is measured in the lab, that data has uncertainties due to reasons that we discussed before, like mainly baseline shift and internal standard in the flash oil. And in that case, the molar distribution model nowadays, it is a very good tool to quality check your lab reported compositions. And in that, so what generally we do, we generally develop a field-wide gamma distribution model, tuning the good quality lab reported extended GC data. And then this tuned model, it can help us to QC any bad quality GC data, gas chromatography data, and systematically we can replace any bad GC data with reliable estimates from the model. And we will see some of the examples of this in the coming slides. So now we have two kinds of models. So one is the discrete exponential model, and the other is continuous gamma distribution model. And we will see why with the exponential model we are saying it's a discrete and continuous with the gamma model. So first we can discuss the discrete exponential model briefly. So this exponential, it's a discretized exponential model, and that's why we call it discrete, because it's only applicable to single carbon number fractions. So you cannot use the model to describe the molar distribution of the heavier ends if you don't have single carbon number So let's say if you have TBP data with non-single carbon number cuts, let's say you have TBP data with only the cuts that are representing different refineries, refinery cuts like gasoline, for example, or light oil, heavy oil, these kind of cuts, then you cannot use this discrete exponential model to describe the molar distribution of those heavy ends. The other limitation of the discrete exponential model is that the difference between the consecutive component molecular weight, so I plus 1 and I, it should always be 14. So if we have a component C7 and C8, then the difference between the molecular weight of these two components should always be a 14 number, which may not necessarily be the case in the real life. Yeah, and this again, the exponential model, as the name suggests, that it's only valid for exponential distribution, which means that if your data falls on a straight line, if you plot the log of Zi versus Mi, then your data should fall on a straight line, and this is usually reasonable assumptions for C8 plus or C10 plus. Extended GC data in most petroleum mixtures, but what we have found that generally this distribution is not exactly exponential. And as Matthias was saying, that like in the gamma distribution model, if you use alpha is equal to 1, that's exponential. But what we have found, at least in the unconventionals, that alpha is generally a 0.5 to 0.7 value for C7 plus. So, yeah, and surely for biodegraded oils, and if you want to describe the molar distribution of oil-based muds, then you cannot use the exponential model, because that data for biodegraded oils, that this distribution of the C7 plus, it's never on an exponential distribution. Okay, so now we can just look at briefly on the model, and that's also in chapter 5, I guess, in the monograph. So what the model, so how the model looks like. So this is the expression of the model. So Zi with a hat, that's the normalized mole fraction of a component. So that's how this is the normalized mole fraction. The mole fraction of the component divided by the Cn plus or mole fraction, which could be like, for example, C7 plus, the total C7 plus mole fraction. So that's this number here, and this is the normalized mole fraction of the first carbon number from which we are using the model. So this could be, if we are using like for C7 plus fraction, the model, then this will be the mole fraction of C7 carbon number itself. And then A is generally representing the slope of the straight line in the exponential model. So that's this number here. And in the model, this is this normalized mole fraction of the first carbon number. This can be calculated with this equation here. So if I replace this whole term into this term A, you will see that A, which is kind of slope of this exponential model straight line, it is mainly a function of this number here, which is the average molecular weight of the C7 plus, for example. And then H is actually a constant. You will see what it is. And N is just the carbon number from which we are starting. So the model starts from N plus 1 until N minus 1. For example, N is it could be C7, for example. And also this the molecular weight of each component, that's given by this equation here. Mi is equal to 14 I plus H, and which again suggests that this delta M, the difference between the two consecutive component molecular weight, should always be 40. That's why this assumption comes from here, because the individual component molecular weight has to be given by this equation. And H is a constant, and PVT-Sim by default, I think it's -4 value. And what H is actually suggesting, if we just take one expression here, so if we take this expression, so this is the normal paraffin molecular weight of carbon number I, and this is the average molecular weight of carbon I. So we know that the normal paraffin molecular weight for any carbon I is given by this. So let's say that could be for C7 component, that will be the normal heptane, and normal heptane is about 100. So yeah, so if you take, like, if you put I equal to 7, you will get about 100 with this expression, minus this is the 14I plus H. So if we solve this expression here, you will get 2 minus H, and 2 minus H, that is representing the difference between the molecular weight of normal paraffin versus the single carbon number average molecular weight. So if in PVT-Sim, if it's -4, if I put -4 here, then what it is gonna suggest, then this -4 is gonna be a value of 6, and this 6 will suggest that the molecular weight of average carbon number, or average single carbon number, is 6 units less than its respective normal paraffin molecular weight. And that will be a constant value for all components. So the molecular weight of C7 will always be less by 6 units from normal C7, and for C8 it will be less than 6 units from its respective normal C8. So these are all limitations and assumptions in the exponential discrete model. And you will see in the gamma distribution model, there are no such assumptions. And if I plot, for example, this is log of Zi versus the difference in the carbon number. So that's how my data looks. And then what you do is you just fit a straight line through the data. So that's this straight line, that's your model. And the amount of the heaviest fraction, this is Zn plus, so N is the heaviest fraction we have. That is just calculated by 1 minus sum of all mole fractions until n minus 1. So that's the lab reported Zi, and that's what you have calculated from the model. And this is the amount of the first carbon number that comes from this equation here. And A is mainly representing the slope of this line, which is mainly a function of the average molecular weight we have seen before. So higher the average molecular weight, for example, for oils, this will be less steeper, this straight line. Yeah. Okay. So now we will discuss the gamma distribution model, which is a more general model, and that's something we use. And you can easily transform the gamma distribution model into an exponential distribution model. So so gamma distribution model, why it's called a continuous model compared to the exponential model, which was discrete, is because it is a continuous function of molecular weight. It's just a probability density function, which is a continuous function of the molecular weight, and it has 3 parameters, as Matthias said. One is the shape factor, that's this alpha, that controls the shape of the distribution. So if I plot log of Zi versus M, if alpha is equal to 1, then it's a straight line. Alpha 0.5 looks like this blue line, alpha equals to 2 has this hump, which is the green line. And this eta, that's the second parameter in the model. That is actually the lowest molecular weight you can have in the distribution. So that's the molecular weight on the x-axis from which you are starting your distribution. And then they have the third parameter is average, which actually comes in this beta term here. And the average molecular weight, again, that will be like if you are doing the molar distribution for C7 plus, then that will be the average molecular weight of the C7 plus. Okay, so that now we will discuss something that was not mentioned before, and it's because we now see that the gamma model is a continuous model, right? So this is, if you have these three parameters, alpha, eta, and the average molecular weight, you get this continuous distribution of the component amounts versus molecular weight. But we never use the gamma distribution model in its continuous form. We always need to discretize it to represent the different components we have. And that's the beauty of this model, that you can actually discretize this continuous function in any intervals representing the different cuts or components you might have from your laboratory PBT analysis. So yeah, so the gamma model is almost never used in its continuous form. It needs discretization. Yeah, so this is maybe this looks very complicated, but the simple idea is that this continuous distribution that you see here, it needs to be discretized. And to discretize, you need some kind of boundaries. You have to specify the boundaries on x-axis, which we call as lower molecular weight. So we represent them as this MLI here, and in this monograph it is MBI. So it's the same thing, MBI or MLI. So that's the lower molecular weight boundaries that is specified for each fraction or cut that you are interested in, and that so that will discretize this continuous function. And once you discretize it, then this area under the curve, so this shaded area, that is gonna give you the amount of that component that you are interested in, and also it also gives you the average molecular weight of that component. So this is the equation from chapter 5 in the SPP monograph. Yeah. So in summary, to use the gamma distribution model, you need three parameters: alpha, eta, and the average molecular weight that describes your continuous distribution. And then on top of that, you need some kind of boundaries to discretize your continuous function, which we call as lower molecular weight boundaries. And the choice of lower molecular weight boundaries depend on what kind of fractions you are interested in. If it's only single carbon number fraction, those molecular weight boundaries may be different. If those are lump fractions, for example, refinery cuts from the TBP data, those boundaries may be different. And there are different ways of finding those boundaries. And yeah. So how do we come up with the gamma model parameters? Like how we determine what's the alpha, eta, for example, average molecular weight, and these molecular weight boundaries. So the data that can be used to determine those numbers, it could be either your TBP distillation, it can be the single carbon number cuts, that is from this ASTM D2892, or it could be other cuts, for example, the refinery cuts. That's more common type of PBT data that people generally have. The process people usually have that data. But usually we recommend that if you are doing the TBP distillation, SCN cuts, the single carbon number cuts, C7, C8, C9, those are the best. And the main reason is that it, like it was the question before, that how you integrate the TBP data and the GC data, like using TBP data for the heavier fraction. So if you have single carbon number cuts for your TBP data, then it's much easier to integrate the TBP data and GC data together because you have the same kind of components in both data. But if you have other data, like if you don't have TBP distillation with single carbon number cuts, still you can use the TBP data and make most of the data in the C7 plus characterization. So that's one source of data, and here we know that we get the average molecular weight. Oh, yeah, Gerardo, you have a question?
My microphone again. Yes.
Yeah. Okay.
There is. Yeah, I was eating, so the microphone is off.
No.
There is this rule that says, you know, when I have a subsea and I'm going to connect to a host, we try to mimic their carbon cuts, right? Their single carbon number cuts. I'm never understood the reason why, but it's a very common rule to try to have all the fields within the same single carbon number. Could you elaborate a bit on that?
Actually, unfortunately, I didn't understand the question correctly. Maybe you can elaborate.
Yeah. So let's say I have field A that I'm going to be connecting to a host that has field B, C, and D.
Okay.
And many times I'm being asked, can you do the equation of state with the single carbon numbers cuts equal to field B, C, and D?
Yeah.
So then when we start looking at the system as a whole, it becomes easier. But I never understood the reason behind it.
Yeah.
Is it clear now?
Yeah, very good. And it's a very good and very valid question. And yeah, so
can you restate it as you see the question, Bilal, first?
Yeah, I think what I have understood from Gerardo's question is that like if you have different fields, for example, field A, B, and C, and when you are developing equation of state models, why it's generally asked or recommended to develop an equation of state model on a single carbon number basis, for example, for the different fields. Is that right?
Yes. Yeah, that is correct.
Karis, do you want to comment on it? Or
no, I think you can go ahead. I just wanted to make sure everybody was on the same.
Yeah. Okay. Yeah. So I think it's mainly because like if you have single carbon number, and that's like one reason or one of the many reasons why when we develop equation of state models, we always develop a very detailed equation of state with as many components, single carbon numbers as possible with the entire resolution that we get from the lab. Reason why it's usually recommended or it's done like that is because when you have different fields and when all the different fluids will start flowing together, then you need you need a PVT model that can describe the mixture of the different components as well. So like, for example, if you would have developed equation of state models for the different fields, and those equation of state models might have different components, like different lump components. One field A might have 11 component equation of state model where each component is different than field B. Then if you want to, if you are doing process calculation, for example, when all the streams are commingling, so for that mixture of the stream, which and each stream is coming from different field and each equation of state model has a different component, then you would need to stack all the equation of state models together on top of each other to be able to process that mixture of the stream. I don't know, Curtis, if I explain it in an easy way, but you can comment on.
Well, there's I guess the one question is whether the fluids from A, B, and C are going to be mixing either in the reservoir or in the surface.
Yeah.
Right.
Yeah, I
And if
assume
it's
it's in the surface. Yeah.
Yeah. So if not in the reservoir, then in theory you could have somewhat different, maybe the same component molecular weights, but the properties of each component might be somewhat different. Okay. But because you need to allow the if there's mixing in the reservoir, you basically need a single component slate, right? And generally a set of properties that don't vary from area to area. If there's mixing in the reservoir, and the mixing might be happening in the wellbore or through the wellbore, right? Layers A, B, and C might not be communicating vertically, but as you start putting wellbores in there and you're commingling production from A, B, and C in a single wellbore, shut the well in, you're going to get all sorts of mixing, right?
Yeah.
Yeah.
So you need the common set of components for that reason. If it's only mixing at the surface, then you might get away with having even different equations of state for A, B, and C in the reservoir. It's not uncommon to happen that people do it that way. Whether it's necessary is another question.
Okay.
Yeah. But but in that case, if all the fluids are commingling at surface, you need a common US model for the surface, right?
But then you can just compound the three different equations of state into one that assumes that they're all the same, either Payne-Robinson or SRK.
Yeah.
But then you can just composite them in together in HYSYS, for example. That's very common for a lot of the companies in the North Sea. They do it that way.
Yeah, because they ask us for that, and yeah, now I understand it's out of convenience, but it's not necessary because I didn't understand it initially.
Yeah, so if it's mixing only at the surface, then it's not necessary to have the same US in all the reservoirs. But if you have mixing within the reservoirs or through the wellbores, whatever, then you need to have the same equation of state, preferably the same component slate for each of the reservoirs.
Thanks, crystal clear. Yeah.
Very good. Yeah. So we just continue with the gamma distribution model. Yeah. So on this slide we are discussing how we determine the different gamma model parameters, and so if we have these are the two kinds of data that we can use. You can use TBP distillation data or the gas chromatography data. And in the TBP distillation data, we generally also have the average molecular weights measured. And since gamma model is giving us the average molecular weights, we can tune the gamma distribution model not just to give us the right measured good quality weight fractions, but also the measured average molecular weights. And the way we do it is if we have these kind of data, we generally tune this field-wide gamma distribution model with the alpha. That's what Matthias is trying to say. And the shape factor, the bound, and this lower molecular weight for each carbon number, they are usually the same for all the samples. So if you have like 50 or 100 samples from a given field, for all the samples, we try to have generally we try to have these three parameters same for all components, and then the average molecular weight, it will be different from one sample to another. So let's, for example, for gas condensate, it's usually smaller compared to the oils, for example. Yeah, so this is one example that's one of the studies we did, and you can see like these are the two samples. So that's you can say that's an oil sample. It should have been green, I guess. And this is the gas sample, the gas condensate, and you can see that the distribution, the motor distribution, it has the same shape factor for the two for the two samples, it has the same bound. The average molecular weight is actually different, and the lower molecular weight boundaries to discretize the gamma model is also the same for both. And you can see how with the same shape factor and bound, it is giving us a very good match of all the lab data. And here, like for the gas sample, you can see that the lab reported data is deviated quite a bit from the gamma model. And in that case, we can replace the bad lab reported data and trust more on the gamma distribution model, because we have tuned that model to tens and hundreds of samples that we got from that particular field. So this is one example how the gamma distribution model can be used in today's scenario when we get the extended DC distribution. It can be mainly used for quality checking the lab data and replacing the bad quality DC data. So there are some.
Just one question before you go forward.
Yeah.
It's with regards to the alpha value. Do you have any recommendation for us to choose this value? So apart from the biodegraded oils, so we know the value is quite high. But for a normal black oil, so do you have any recommendation for that?
Yeah. So that's I think what we are trying to convey. The message what we're trying to convey here is that if you have extended DC data for many samples from a field, you can actually tune the distribution model and find out what is the best shape vector that you should use for that particular field. Curtis?
Yeah, I think we have to put this in the context of people not having software that actually allow you to do the gamma modeling, the fitting of the GC data to the gamma model. There's really not any software other than one that we use that allows you to do that.
Yeah.
And we need to respect that when we answer this question.
Yeah.
So what I would say is that you can do all of this gamma modeling in Excel. It's relatively simple. We have Excel sheets that we can exactly do this kind of process to come up with the shape and to do all of that gamma modeling outside the PVT software. That's one way to do it. If you're interested in that, then basically flag us with a mail or something, and we can have maybe an offline session on how to do that, or some of the Excel sheets that we'll be using, maybe you'll actually see how you can do that. That's one option. The other is that you simply use the laboratory data anymore. You get all this extended data, and you only use the gamma modeling to, in a sense, identify problems with the GC data and correct those problems again offline. So you correct the composition. Out to C20, it's got a great fit of the gamma model, but it's falling way below the extrapolation and the data. So there's baseline shift problem, something like that. So you have an option to do, again, offline in Excel or some other program, the correction of GC data. If there's no correction needed, we just use the data. So, and then you should also be aware that PVT-SEM doesn't have anything but alpha 1. So you don't have any real choice other than modeling it externally in Excel or something and importing that distribution into PVT-SEM. You would have to do it manually. So the option is to do it with the equations and something like Excel. We can give you a template externally to make use of it, either for QC or replacing bad data. It seems to be bad data, or going to the software that we use, the PhaseComp. And in that case, if you have PhaseComp and can do all this automated within the software, then you basically, what Bilal is saying is that you take all your GC data in and you fit to the gamma model each and every sample in a consistent way. and it becomes part of that whole EOS tuning process. So if you're using PVTP and they, you know, I don't know what they have in the way of options, but you know, you won't be able to do this within any of the other softwares, I think. So you have to decide what you want to use the gamma modeling for.
Yeah, thanks, Curtis. And as Curtis was saying, that this can be done in Excel, and that's something we are also aware of, that gamma modeling is generally not available in other PVT packages, like at least PVT-Sim, which most people use. So that's why, like tomorrow when we do the exercise on equation of state model development, we will use a very comprehensive Excel file where we will do the entire C7 plus characterization, and that Excel file also have this gamma distribution model program in it, and we will see how we can use that spreadsheet to develop the gamma distribution model for the PVT reports we have, and that template you can also use for your other fields if you want. Okay, so I think we can move forward. Yeah, this is just a slide giving you the orientation of where you can use the gamma distribution model, and just highlighting that it can be used for the molar distribution of any petroleum mixture, whether it's a typical single carbon number compositions for the samples we have. It could be an oil-based mud composition. It can be refined residue. So you can see there are different pictures taken from the monograph. Yeah, so that's a good comment here. PVTP actually has a gamma distribution model, and there you can specify these two parameters, the alpha and the beta, which we saw before. Yeah, but again, the PVT, that's another debate. How, like in PVTP, you can see this gamma distribution model there, but they don't tell you everything about how they are using the gamma distribution model, because for the gamma distribution model, it's not just these three parameters, alpha, eta, and the average molecular weight. You also need to define the lower molecular weight boundaries. And I don't know what lower molecular weight boundaries they are using for the discretization of the gamma model. Maybe we have to go through the manuals to see how they are implementing that. Okay, and this is a and that's a good comment from Curtis, that if a software has a gamma distribution model, like for example, gamma distribution model, then you still need to know what are these gamma model parameters that you should use to define that you should use to define these define the distribution of the heavier ends, like alpha, what's the alpha factor for the given field, and the eta, the lower bound for the given field. And in that case, like Phasecom has the capability that you can use gamma model parameters as a regression to match your GC data, for example, but PVTP doesn't have that capability. So you have to still have to use the Excel sheet to find out what are the gamma model parameters representative of your field, and then maybe use it in PVTP for the distribution. Okay, and this is again one other example of bad quality GC data. We have a gamma distribution model, and you see these components going down like this, indicating some kind of baseline shift error or internal standard error in the GC data, gas chromatography data measurement.
Just an example like that, Bilal, if just a question we typically get at this point is, how do you know in this graph right here that it's the lab data that's wrong,
yeah,
and not the gamma model?
Yeah. So, and again, that's a very good question, and we get this question a lot of time. And the reason why we suspect the lab data and we believe more in the distribution model is because we know that the distribution model that we have come up with, it is tuned to a very wide range of sample compositions. So if you have like 50 or hundreds of samples and you have tuned your gamma distribution model with a single alpha value for all the samples and the lower molecular weight boundary for all the samples, then you know that that alpha or shape factor is representative of your field. And if there are among hundreds of samples, if there are like 10 or 20 samples that are not following the distribution trend, then you start suspecting the lab the distribution.
What if you have a case where you have very few samples?
Yeah. In case of few samples, then then you should like few samples, meaning that you have like only 2, 3 samples or 4 samples. In that case, you have to be careful in using the distribution model, like because then you may be tuning your distribution model with data that have more uncertainty, and so in that case, we generally recommend using the lab reported data as is in the US model development, at least the extended GC data, without any correction from the gamma model.
Good.
Yeah. Yeah. So the molar distribution model, gamma distribution model, that can be developed. The GC analysis, if you have GC analysis until C36 plus, for example, that is relatively cheaper compared to the DPP distillation. And these are the two different data types that you can use for the distribution model development. The exercise we have here, it's not super important to do, and then we'll just skip that. And we have a more comprehensive exercise on the gamma distribution model development tomorrow that we will go through. So we can just take a break now. If there are any questions, maybe we can answer those first and then just take a 10-minute break.
Okay. Meet back at 2 in 13 minutes.
Okay. Yeah. 13 minutes, as Matthias says. Okay, so let's okay, there is a question already.
Yeah, one question came to my mind during the break when I was digesting the gamma model.
Yes.
You said that in PVT-SIM, gamma model has one default alpha value, which is equal to 1. Is this a problem when we work with biodegraded oil?
Yeah, the first thing is that PVT-SIM doesn't have a gamma model. It has an exponential model, which is essentially the same as if you use a gamma model with alpha is equal to 1. So that's one thing. And the other thing is that, so if you have biodegraded oils, so one thing we know about biodegraded oils that the C7 plus distribution of those oils doesn't follow the exponential model. So now if you are using PVT-SIM exponential model to model the distribution of those heavier ends with an exponential model, that will be very wrong, I guess. But if you are using just the lab reported composition in the PVT-SIM and without using the exponential model, I don't know if you can do it in PVT-SIM. Then I think it should be okay.
Okay, thanks for clarification.
Yeah, Curtis?
No, that's right. You just have to use the measured data.
Yeah.
Distillation data or GC data.
Okay.
Another question from Thomas.
Yeah, Thomas? Thomas, do you have another question?
No, sorry, I have forgotten to lower my hand.
Yeah, no problem. Okay, so I think we can start. We can start the next topic. That's equation of state models, and here we will go through the fundamentals of the equation of state model, so that when tomorrow when we'll be developing the US model, we will know what is an US model, what it is composed of, what does the different parameters mean, when we will look at the equation of state. The two tables that Matthias mentioned on the first day, component properties table and the binary interaction parameter table. So we will know what do they mean, what each component property means, and how the different properties affect, for example, the phase behavior. So in this presentation, we will go through like the simplest equation of state we have for the gases is the ideal and real gas law. We'll start with that, and then we will jump into the cubic equation of state models, and there will be a bit of history, and Curtis can talk about the interesting stories about the history, of course, and then we will see how the equation of state models can be used for single component, and then we will have this volume shift factors. We will see what are these and why do we need them in the US models, and then we will go into more complicated phase behavior where we have multi-component systems. We'll see how the US models are applied to such systems which we generally see in our petroleum system. Yeah. So as an introduction, these are just the book definition of equation of state. The examples are like the gas laws, as I said. These are the simplest equation of state. You have cubic equation of state models that we generally use, Peng-Robbins and SRK. Those are our cubic equation of states. And then we also have some non-cubic EOS or soft EOS models that are not discussed in this course. Yeah. So the ideal gas law, everybody knows, PV equals to nRT. No need to have a long discussion on that. In the gas law is applicable to ideal gases, like very low pressures and high temperatures where the gases behave ideally. And then we have a real gas law, which where we have this gas Z deviation factor, or the gas Z factor, which accounts for this non-ideality of the gas, and We know that Standing Cards, who have developed this chart for the gas Z factor, that can give us very accurate values of the gas Z factor, and that's the only thing you would like to know for the gases to describe the PVT behavior of the gases. So the gas Z factor is the fundamental property in describing the phase behavior of the gases. For the liquids, we have we only have this PVT equation. That's the isothermal compressibility, describing the single phase pressure, volume, and temperature relationship for the liquids. So really, what we need a PVT equation that is applied to both gases and liquids at the same time, and that is achieved by this cubic equation of state model. So it's the same equation of state, or same equation that describes the pressure, volume, and temperature relationship for both gas phases and liquid phases. And in terms of the Z factor, we can write this equation like this. So this is why it's called cubic, because it has this cubic power. So the highest power in the equation is this cube here. So that's why these are cubic equation of state. And then in the equation of state, we have different coefficients for each of these polynomial terms. So it's one here, A2, A1, and A0. And we will see, like, for example, when we'll go through the different US models, Pang-Robinson, SRK, or Redlich-Kwong, like how we can calculate these coefficients, which are written here. So these will be different for different equation of state models, and they are mainly function of pressure, temperature, the composition, and the component properties, and they are formulated differently for different equation of states. The other important comment is that here you see the cubic equation of state model written in terms of the Z factor, but this can also be written in terms of the molar volume, where we know that the Z factor can be equated to the molar volume. So this V is actually the volume divided by the moles. So that's the molar volume. Generally, the EUS models, they are written in terms of the Z factor, because when you solve them in any PVT package, you generally prefer to solve them in terms of Z factor because it's more convenient and more efficient. So that's why here you see in terms of Z factor. But when we will discuss the different equation of state models, we will see that those are proposed in terms of the molar volumes, and then you can easily transform them into the Z factors for thermodynamic calculations. Yeah, so again, the cubic equation of state models, they can be applied for both liquids and gases, and also it can be applied for pure components, and also mixtures with some assumptions and mixing rules that we will see later on in this PowerPoint. Most common equation of state models that we are generally aware of is the van der Waals. That's the first cubic equation of state model developed in 1870s. Then Redlich-Kwong developed or modified, actually, the van der Waals equation of state model. So this is, you can say, this is kind of a parent cubic equation of state models, and all these models that came later, these are just modifications to van der Waals for different applications and purposes. So van der Waals, that was the first cubic EUS in 1870s. Then Redlich-Kwong modified it for, we will see, and we will go through that, for mainly for gas processing. Soave Redlich-Kwong EUS, it's actually the same EUS as Redlich-Kwong, but with more generalized correction. We will see also later what are those corrections, and the applicability of the SRK EUS. It was in 1972, and then 1976 was Pang-Robinson EUS. Yeah, so we will discuss these EUS more in detail later on. Yeah, so first we will see how these cubic equation of state models, the different ones, SRK, RK, Peng-Robinson, how they are applied for single component, and then we will move to the more complicated multi-component systems where the same EOS models are applied, but with certain mixing rules. The van der Waal equation of state. So yeah, again, it was the first cubic EOS. The two parameters in the equation of state model are the A, this is a small a and small b, and you need these two constants to relate the pressure, temperature, and the volume for a given component. So if you know A and B, for example, for water, you can calculate, for example, at any pressure and temperature, what's the volume of water, for example. And A and B, so A is generally called as the attraction term, and this is the repulsion, the B parameter. And what you can also see from that equation, that if you increase the pressure to infinity, this expression here, this equation here, the volume will become the B term, and that's the minimum volume on a molecular scale. So that's the minimum volume that a component can have at any at these infinite pressure. So it's not the zero volume, which is the assumption in the ideal gases. Also, like if we decrease the pressures and if the pressure tends to be zero, then you can see also from this equation that this equation will transform into P equals to RT over V, which is the ideal gas equation, PV equals to RT. And that's something we know, that at very low pressures, gases behave ideally. So those are like two special cases of this cubic EOS. Yeah, so just to be aware that the A and B, these are constants, and these should be constants for a given or a particular component. These are just the units, for example, for the two parameters, and this should be fit Q actually. So this has B has the same unit as the molar volume. So now the main question is, like, if we want everybody now, and yeah, now you know that the cubic equation of state model, to make use of the cubic equation of state model, at least there's van der Waal, you should know the A and B values for a given compound. So if I ask you, like, for example, if you have water, and if you want to know the value of A and B, for example, for water, how would you come up with those values, for example, for water? Any suggestions from the participants? Anybody want to share some ideas here? And so if you want to know what are the best values that we should use for A and B, for example, for water, to use that van der Waal equation, how can we come up with that? Yeah. Okay. So like one way of doing it, for example, is that that's like the general way we usually think, is that if you have some kind of data measured for water, for example, and we have a lot of data, phase behavior data measured for water, we have steam tables, vapor pressures measured as a function of temperature, we have saturated liquid and vapor densities at different temperatures. So we have a lot of data measured for water as a pure compound. We can use that data and try to find out the best value of A and B by matching or using the van der Waal equation of state to better predict all that data. So doing it. But one issue in doing that is that first it's a lot of work. Like you will be using a lot of data and try to tune your cubic equation of state model and come up with a single value of A and B. And the other is that if that work is, for example, done by Matthias or Curtis or me, we may come up with different values of A and B, because that tuning of the cubic equation of state and the tuning of A and B value will depend on which data, like when I'm doing the regression, which data I'm weighting more, or Matthias thinks is more important, for example, or Curtis thinks is more important. So we may come up with different values. So van der Waal, he has this great idea of finding the unique or specific values for A and B for any given compound. And what he said that if we like draw pressure volume diagram for a given component, so we know that it looks like this line here. So that's at given temperature, where the temperature is less than the critical temperature of the compound. That's how the pressure volume diagram looks like. And if we continue to increase the temperature and make the same pressure volume diagram, we know at critical temperature there is only one inflection point where we have both the saturated liquid and saturated vapor phase coexist. So that's the critical point we have, and this is the phase envelope. That's this dotted line here. So what we know about this this critical point here on this pressure volume diagram, so that's just the higher greater than the critical temperature. What we know at the critical point, that we can write the van der Waals equation like this, right? So this is just applying the equation at the critical point. So P is replaced by the critical pressure, temperature is replaced by the critical temperature, volume by a critical volume, and we have the same A and B. The other thing we know about this critical point is that if we take the derivative, the first order derivative of this equation with respect to volume, then it should be 0, because there is just one inflection point here. And the second thing about the critical point is that if we take the second order derivative, that should also be 0, because now after the critical point, it's this function, the pressure volume function, is monotonically decreasing. So we know these three things about the critical point. So now we can, with these three relationships or equations, we can develop three equations with only two unknowns. So we have A and B, which are the unknowns, and we have actually three equations to solve for. So now this is if we can solve these three equations in different ways, and we can come up with three sets of A and B values. So we can solve, for example, the first two equations and come up with this A and B, which is the A and B from the critical volume equation and the TC equation. Same, if we can get the A and B values from critical volume, critical pressure, and critical temperature. And these will be the different values of A and B. So what van der Waals suggested is that van der Waals said that we can use the value of A, B from the critical conditions. So the critical pressure and temperature. And he said that he just neglected the A and B that could have come from the critical volume. So we got the A and B values here. If we solve, for example, these two equations here, the TC equation and the PC equation, we get these values of A and B. And we will see later on what happened, what was the consequence of neglecting the critical volume term, and how can we actually correct for that consequence. That's something we will see later. So these are the A and B values for any given compound, and you can see from these equations that if you know the critical pressure and temperature for a given compound, you can calculate A and B, and that will be a unique value of A and B for a given compound. So for example, for water, we know what's the critical pressure and critical temperature. So knowing that, we can calculate the exact value of A and B, and that should be unique to water. So if we now know that A and B are defined by this, then we know that VC is equal to actually 3 times B. So the VC now, if we replace the value of B that we have calculated before, so VC now will become 3/8 R times TC over PC for a given component. And if we calculate the critical Z factor, which is simply PV equals to NZRT, and each pressure, volume, and temperature are critical properties, then we can find out that this is just a constant value, 3/8, the critical Z factor. So critical Z factor in this van der Waal equation of state model is 0.375, and you can see that it's just a constant value. So it's not a component dependent number. It's just fixed for all components, and that is actually the consequence of neglecting the critical volume term. So when we neglected the critical volume term and we only use the TC and PC, that's what happened, that now the critical Z factor is fixed for all components, and that's not the case actually. So if you look at, for example, methane, it has a critical Z factor of 0.28, and generally if you go towards heavier components, it decreases. So this is actually far removed from the hydrocarbons that we are generally interested in. And van der Waal, he was not like when he was working on the cubic equation of state model, he was not interested in using the EUS models for the petroleum mixture. So that was not a big deal. And but what happens with this, like yeah, so these are just the forms of the van der Waal. So this is the van der Waal equation. So that is now the coefficients. So B plus 1, that's the coefficient for Z square, and A is for Z and AB here. And the way we define A, the coefficient here is the small a times pressure over RT square. And we already know what is the value of A, so we can bring that. So it's to reduce pressure to reduce temperature. And same goes for a capital B. Now it's a function of pressure and temperature, and also the small b. And these numbers here is 27/64. That's a constant number, and this is also constant number. So this is the omega A and omega B. So if you, like we will see later on, this is omega B and this is omega A. So these are generally termed as omega A and omega B, and these are constants for all the components in a cubic equation of state model. And these constants, the values of these constants will vary from one equation of state model to another. Yeah, so this ignoring the critical volume term to derive the value of A and B, the component VC now is defined by the 3B, 3 times B, and the ZC, the critical Z factor of all the components have become constant. And this has led to, like, if you start calculating the densities or molar volumes, the liquid phase molar volumes at all conditions, so it leads to high deviation compared to the lab data, and the liquid densities were predicted very low. So like if we use, for example, the van der Waal equation of state with the A and B given by the van der Waal, what we will find out that if the liquid phase densities, they will be predicted about like 40-50% lower compared to the lab data, because the molar volumes are predicted higher because of the fact that the ZC value is about 0.375, which is quite higher than the normal expected ZC value of these hydrocarbons that we have, which is starts from about 0.28 for ZC of C1, and it goes lower. And it mainly affects the liquid phase densities and not the gas phase densities, and that's something we can see on this plot. That if you plot pressure volume diagram, so this black line is the expected phase behavior of the of a particular component. Maybe it's water. We can just say it's water, for example. That's the expected or the lab measured, for example, data. And if we use the cubic equation of state model, that's how it will be predicted. It will predict the right, for example, the critical point. So that's for example, this is the critical point. So this is gonna be PC, and we are doing it at TC. It is gonna predict the right PC and TC because those are the inputs in the equation of state model to get the A and B. So it should predict the right critical temperature and pressure, but the critical volume is gonna be with an equation of state model, it's gonna be much higher than the expected value, and this is gonna drive all the liquid phase. So here on the left side of the critical, we have liquid phase. On the right side of the critical, we have vapor phase. So on these liquid phase densities, they are gonna be much lower because the volume is higher, so about 30–40%. But the gas phase densities are not much affected because like small difference in the volume here is not gonna translate into much error because the volume itself are much higher. There the magnitudes of the volumes are lower, so the small differences will will end up into a large error. Okay, so now we jump into the Redlich-Kwong equation state model, which is kind of the first US model where people actually started using the cubic US models for petroleum applications. Any questions until now? Anything that's not understood or somebody wants to know more about something? Yeah, okay. Yeah, so Redlich-Kwong equation of state. Yeah, Curtis, do you want to speak out a bit about the history, like what was happening at that time, and yeah, just
49 was when Redlich-Kwong was presented, and that's the same year that Muscat and McDowell published this flash calculation for separator design and petroleum applications, but using fixed known K values. But basically, this was the age of computers starting to be used in science, engineering. So that's the backdrop for the Redlich. I think development became very important, but is related to the post-war, the computers starting to be used.
Yeah, and the main thing that Redlich-Kwong and their group was interested in is to get the like they wanted to use the cubic equation of state model to get better phase behavior of these lighter components because they were working on this gas processing calculation, and they were interested in calculating the accurate liquid yields at surface. So they were very interested in getting very accurate phase behavior of these lighter components, which we usually see at surface and they end up in the gas phases. So yeah, so this was the objective for them, to modify or come up with a cubic US model that accurately predict the C1 and lighter hydrocarbon phase behavior more accurately. So they proposed two modifications in the van der Waals equation of state. These modifications are highlighted in blue here. So this was one modification, that's this alpha term as a function of reduced temperature. So that was one modification. The other one was this term here, so they added in the denominator with V square. And the two two modifications have two reasons. And this whole term here, A times this alpha, the correction term, is now written as A of RK. So that's Redlich-Kwong A. That's being modified from the A value given by the van der Waal. So yeah, before we go into the reasons of these corrections, this is just how the equation of state looks like in terms of the z factors, and you can again see that these coefficients are, this coefficient is a bit different than the coefficient that we saw in the van der Waal. And A, this capital A is equal to, it's again the function of pressure and temperature, and then the small a, and then here is the small b, and then that small a of RK is actually the same as the small a of the van der Waal equation, but then we have this alpha, the correction term, and then we have again the b, and then this omega a and omega b will have different values. So these are the values of omega a and omega b in the Redlich-Kwong equation. And then alpha, what they propose that alpha, the correction term to this a term here, is just 1 over, that's just 1 over square root of the reduced temperature for the given component. So what the reason why this correction term was introduced, it was to improve the phase behavior, or like the vapor pressure diagrams of these lighter components, C1 and lighter hydrocarbons, because they were mainly interested in getting the right phase behavior of those components. And this second modification of adding this VB term in the denominator, that was to get better liquid phase densities of these lighter hydrocarbons, because if you calculate the ZC value of the Redlich-Kwong equation of state, you will find out that it's ZC is equal to 1 over 3. So ZC is equal to 1 over 3, that's 0.33, which is much closer to, for example, you look at for methane, it's 0.28 somewhere. So you can see it's much closer to the methane critical Z factor compared to what we had in the van der Waal, where it was about 0.375. So that's the van der Waal, and that's the Redlich-Kwong. So getting more closer to the critical Z factor of these lighter components, giving it helped to bring in line the densities better, and but still the liquid phase densities of the heavier components, which they were not mainly interested in, they were underestimated. But and also the phase behavior, like if you look at the vapor pressure curves, they were also not satisfactory for these very heavy components, because this alpha correction term, which is very simple, like 1 over square root of TR, the reduced temperature, it was not very reasonable for these heavier hydrocarbons. So after the Redlich-Kwong equation of state model, Suave, Curtis, do you want to say something here about who was Suave and like why he came up with a different?
Well, by, let's see, the early 1970s, I think the SRK was published. And by then, much larger and faster computers were available. And the processing industry, chemical engineers, started using computers to really do optimal design processing for basically optimizing the processing of more valuable products like gas liquids. And Suave is Italian and did this work with the intention for it to be applied to petroleum applications, mostly on the top side. Just as a comment, Redlichen was originally born in Austria, I believe. He fled just before World War II to the United States, and eventually started working at Shell, where he met Guang, who was a Chinese-born who moved with his parents early to the United States, and they started working at Shell, I think, more or less the same time, just before or after the war. And in 1949 came with this Redlich-Kwong equation. And then it was greatly enhanced by Soave, specifically in its ability to predict accurately the vapor pressure curve of individual compounds. That was absolutely the big kind of quantum leap that Soave introduced. A lot of people were trying to do it in the late 60s and early 70s, and what he did was won favor because it was simple, it was very accurate, and it was pragmatic, and then once people started using it, they just continued to use it. So it was, once you get vapor pressures of individual components as a function of temperature, getting the K values of the same components in mixtures was trivial, using the fact that K values were inversely proportional to pressure if you knew the vapor pressure. So you basically could get accurate K values for all components in natural gas and petroleum systems at pressures less than about 100 bar, 1,000 psi, just by knowing that the vapor pressures were predicted accurately. That was the big development by Soave.
Yeah. Very good, and that's exactly what why we discussed all these concepts before, like the K values, the dependency of K values on vapor pressure at low temperature, at low pressures. So we discussed this earlier, that the K values at the low pressures, they are mainly function. If you talk about mixtures, K values are mainly function of your vapor pressure and the pressure and temperature. And if you get the vapor pressure right, it means that you're getting K values right for the different components at pressures and temperatures that are on the lower side for this top side processing facility type calculations. And as Curtis said, that the big side of this Soave equation of state, SRK, it's actually the same, exactly same equation of state model from Redlich-Kwong, but there is an additional correction that we will see. We did not change the fundamental form of the Redlich-Kwong equation of state, but it helped predicting the vapor pressure curve for all the components and not just the very light C1 to very light hydrocarbons component, right? So, and what he did we saw that in the Redlich-Kwong there is this correction term that's alpha that's added to this the term A. So he actually so this alpha, it was in this in the Redlich-Kwong, it was a mainly function of the reduced temperature, but he generalized that alpha correction term to be applicable to all the components to get their vapor pressure correct, and we will see in more detail how that was done. So yeah, so here it's exactly what is explained here. So what he started doing, he started plotting the square root of alpha versus square root of the reduced temperature for the known components, and what he was actually doing. So here you see that you have 3 points. So for example, this is methane, for example, and we know that for example, for methane we have some we have quite a bit measured vapor pressure data. So what he was trying to do, he was trying to use the Redlich-Kwong equation of state model, and he started calculating what is the alpha correction or what is this alpha value needed to get the right vapor pressure at different temperatures. So at this temperature, what is the alpha value that requires to calculate the right vapor pressure? Same goes at this temperature and this temperature, for example. And then and it's just a straight line. And then he started calculating the slope of this straight line. So at TR, that's the reduced temperature, which is, that T over TC. So at TR is equal to 1, where we know that the temperature is equal to critical temperature, there is no correction. So alpha is equal to 1. You see alpha is equal to 1. And the main reason why there is no correction at the critical point is that critical point is the input to the US model. So you provide these two numbers in the US model, TC and the critical pressure. So that has to, at critical pressure or at critical temperature, the vapor pressure has to be the critical pressure from the cubic EOS, because that's the input. So there was no correction at this point, and then you started having more and more correction as you go away from the critical point. And this was just a straight line, and he was trying to calculate what is the slope of this straight line for the compounds where we had the data. So
just a historical comment that he found this relationship between the correction term alpha and reduced temperature, basically plotting square root of alpha versus square root of reduced temperature, produced a linear trend. Once he had done that for a few compounds and found that it was general, I don't remember which compounds exactly he tested this dependency on, but it apparently worked for a wide range of compounds, from hydrocarbons to non-hydrocarbons, water, etc. Once he had that relationship, then all he required to find the slope M of a given compound was a single vapor pressure point on the vapor pressure curve. And what he used was the vapor pressure that was known experimentally for so many compounds at 70% of the critical temperature. And the reason that vapor pressure was known and for a large number of compounds is because there was a guy named Pizzer who had introduced the so-called acentric factor as a term to quantify the kind of the shape of the vapor pressure curve. And it relies also on the 2 points, the critical point and the critical temperature, as being 1 point on the end point of the vapor pressure curve, and then the vapor pressure at reduced temperature of 0.7 was the other point. With those 2 points, you can compute the acentric factor. So what he then did is he just simply went into the tables with acentric factor, found the vapor pressure, and then he found the correction term alpha to match that vapor pressure, and then that gave him the value of M for very many compounds. So that's the method that was used by Soave. Now, apparently, and this I didn't know historically, Jürgen Molderup, who wrote the book with Michelson, he told me just recently that Heng and Robinson, who used the same form of this alpha correction term, and Bilal will talk about it here in a minute, they didn't do it that way. They basically fit the vapor pressure curve of each compound with multiple points to get the value of M, not just using the 1 point from the acentric factor. What Jürgen Molderup claims, I don't know this for myself as a fact, but he claims that the correlation developed for M and the value of M and how that extrapolates was better developed using just a single point than using a series of points. Anyway, the main contribution, I think, of Soave was finding this functional form, being general for all compound types, and second, to then easily compute the value of M and tabulate it for very many compounds based on the known acentric factor. And so that's just a historical note.
Oh, very good. So, yeah, Curtis, thanks for sharing this. I did not know that also. Yeah. Okay, so yeah, so what Curtis is saying here, where's my pen? Okay. So what Curtis is saying that when Suave he started plotting that data, he found that there was a linear relationship between the square root of alpha versus square root of the reduced temperature, and m was the slope. And then he started calculating the slope for many different compounds, where he had the data with at least two pressure points. So one was the critical point, and the other was the critical one. The other was the vapor pressure at the TR, the reduced temperature of 0.7. That is, we will come back to that, and we will start discussing the eccentric factor. So he started calculating the slope with just 2 points on the vapor pressure curve, and so we can just come back to that. So this was the equation that he came up with to calculate, to know the value of m for a given compound, which is a function of eccentric factor, which you will see in the next slide. What is an eccentric factor? But what he found that when he started correlating the slope of that correction line with the eccentric factor, it was a very good function being fit. So so yeah, here is this discussion on the eccentric factor. So eccentric factor is defined, is just a term given to this expression here, which is the log of the vapor pressure with this star, and this is the vapor pressure at the reduced temperature of 0.7, which is 0.7 of the critical temperature. So temperature is 0.7 of the TC, which is close to the critical point. So if you look at this figure, so here, for example, this is your critical point, and then this is your vapor pressure star, which is at the T of 0.7 TC. So that's one other point that you can have on the vapor pressure, and then you have a boiling point here. And what actually eccentric factor is, so if we take, for example, if we have smaller compounds, like for example methane, which are more spherical, you will see that the eccentric factor is more close to the zero value. As we go towards more complex and heavier compounds, the eccentric factor tends to go towards value of 1. And if it is 0, it is telling you how much, what is actually the slope of the vapor pressure line near the critical point. So how rapidly the vapor pressure declines near the critical point. So here you can see for two components, here for just illustration purposes, we are assuming that the two components have the same critical point, just for the illustration purposes. But at this temperature here, how rapidly is the decrease in the vapor pressure? So here the vapor pressure has decreased to this value 0.1 of the critical pressure, and here it has decreased much more, which is 0.01 TC. In that case, the eccentric factor would be a 0 value. For this compound, it would be a value of 1. So next is the Peng-Robinson equation of state. Yeah, so in SR, just to summarize, Redlich-Kwong, the van der Waals equation of state, the cubic equation of state, was the first equation of state with two parameters, A and B. And to calculate A and B, you need the TC and PC of that compound. Then there was this Redlich-Kwong equation of state model. To use that EOS model, we again only need the critical temperature and critical pressure of each compound. But then this Suave, he came up with an equation of state model with a more generalized correction, this alpha, to the cubic equation of state model. And there we saw that now we need another component property, which is eccentric factor, which is this guy here, this omega, represented by omega sign here. So now we need TC, PC, and eccentric factor, three properties for a given compound to do any EOS calculation. So still the cubic equation of state model is defined by two parameters, A and B, but to calculate this A term here, we need we also need the eccentric factor, because the eccentric factor gives us the slope of the straight line correction, and that the slope of the straight line correction gives us the alpha term that's required to correct the A value to get better vapor pressure. So we need three parameters in the component properties: TC, PC, and eccentric factor. And then that's the last thing, and that's equation of state model, Peng-Robinson, and they were Canadian in Canada, where they were mainly dealing with the heavy oil, and they wanted to get better phase behavior for the heavier fractions, and also the better liquid densities for those heavier fractions. So yeah, so this was the equation of state model, and then they have as Curtis mentioned, that they have a new alpha. So the alpha correction term was different than the alpha correction term that was given by Suave for the Redlich-Kwong equation of state model, and one reason why they had to change their alpha correction term is because now they propose a new, fundamentally different cubic equation of state model with additional corrections to the smaller volume here. You see that these are different than the Redlich-Kwong equation of state model. So when they changed the entire equation of state, the cubic equation of state model, they had to come up with new alpha correction term, which predicts better or equally better vapor pressure curves for the individual components for all compounds compared to the SRK equation of state. Yeah. So these are just again, so alpha term, again, it's a straight line relationship with respect to M, but they had to come up with these M values. And as Curtis was saying, that this M value, the slope of the line, Redlich-Kwong, Suave, he found out this value of M from 2 points on the vapor pressure curve, one being the critical point, the other being this vapor pressure at 0.7 TC. But when they were determining these M values as a function of eccentric factor, they tried to match all the data that's available for a given compound in terms of the vapor pressure. And they have two relationship, one for eccentric factor of 0.49, less than 0.49, the other one is greater than 0.49. So if you compare the two equation of state models, Peng-Robinson, SRK, you can see that so like this is methane vapor pressure, this is pentane vapor pressure, and they are like on top of each other. So in terms of the accuracy for individual component vapor pressure, there is almost no distinction between the two equation of states. Yeah, so one big challenge in the cubic equation of state model was to predict the accurate liquid densities, the liquid phase densities. And that again it comes from this fundamental problem that we ignored this critical volume term in defining the value of A and B, and that was proposed by Van der Waal. and that brought up this fundamental problem, the cubic equation of state model, that the oil phase densities with SR Peng-Robinson equation of state model, those were not satisfactory. So the liquid densities were overestimated for all the compounds, and Peng-Robinson equation of state model was better for liquid densities of the heavier compounds because they were mainly interested in those for the heavy oils. SRK SRK equation of state model was better for lighter hydrocarbons. So that's something we can see here. So this blue line, this is SRK, Peng-Robinson, and you can see that the SRK is better, for example, for methane compared to this Peng-Robinson here. And here SRK equation of state model is here the Peng-Robinson US model is better, for example, for pentane, which is heavier in terms of which is heavier than methane. But that was the fundamental problem by that time, that these two parameter cubic equation of state model with only two coefficients A and B was not able to predict good or accurate liquid phase densities. And you can see here these are the vapor phase densities down here, and these are very accurately predicted. They don't have much impact with this problem. Yeah, so we will just look at how the single this cubic equation of state model can be applied for a pure component, and then we will also do a very good exercise on it, which will also give you a better understanding of what a cubic equation of state model is and how the calculations are done, for example, in all these PVT packages for pure compound at least. So if for a single compound, the vapor pressure, we know it's a pressure at the given temperature where we have both saturated liquid and saturated vapor phases that exist at the same time. And the way we can calculate the vapor pressure for a pure compound is that if we plot the pressure versus volume diagram with a cubic equation of state model, it would look like this. This is like a continuous function of pressure versus volume with a cubic equation of state model here, knowing the A and B, and it's a constant temperature. So the way the vapor pressure is calculated. So what we do is we change. So for a given temperature, that's the pressure volume diagram, and we play with the vapor pressure. So we move the vapor pressure up and down, and the pressure value where this area under the curve, so this area and this area under the curve, they become the same. That is called the vapor pressure at that given temperature, because this area here, these are the fugacity. So this is the liquid phase fugacity, and this is the vapor phase fugacity, and these have to be the same, or fugacity is, or we can also say the chemical potential for the thermodynamic equilibrium. So that's the fundamental condition when you are solving the equation of state model. That's the fundamental condition that you need to achieve for a thermodynamically equilibrium solution, that the fugacity of the component in the liquid phase and the vapor phase, they have to be the same when there are two phases. So that's how we come up with a vapor pressure value, that the fugacities of the two phases should be the same at that given pressure. And that's something we will also do in the exercise in the Excel. Yeah, and once we have found out what's the vapor pressure, then generally we just ignore the middle root. So we now know that there are three roots possible. One is this root at this pressure. The other root of the what do we mean by root? Root is the value of the molar volume. We are solving for molar volume of the Z factor. So one is this root, the molar volume. The other is this, and the third one is this. We ignore the middle root, and the minimum value is taken as the as the molar volume of the liquid phase, or the gas, or the Z factor of the liquid phase, and the higher molar volume is the vapor phase molar volume. So these are just the same slides explaining the similar thing. So we can just do, yeah, we can take a break, I guess, and then after the break we can do this exercise together, calculating the vapor pressure and equilibrium phase densities with the equation of state model for just using water as a pure compound. Okay. Yeah, just take a 10-minute break. Yeah, okay, I guess we can get started with the exercise that we have on this topic. And the objective of the exercise will be to see how the equation of state models are applied for single component, and to get ourselves familiar with the different parameters in the equation of state model. And for that purpose, we will be using the SRK equation of state model. And just forget about what is written here. So just forget about this here now, and we will see what it means in the coming slides. But what we'll be doing in the exercise is using the SRK equation of state model for a pure compound like water, and calculate the vapor pressure and the equilibrium phase densities. And before we do the exercise, there is something that I want to highlight, and because it's I know it's a kind of a dry topic, and it's the end of the day. So, but the one thing that we had been mentioning before, that for equation of state model development, or for equation of state model calculation, k values are very important. Like that's the fundamental thing in equation of state model calculation. But when we are discussing equation of state models here, we haven't seen k values being used anywhere. Like when we discuss, for example, the SRK-US Peng-Robinson equation of state, or Redlich-Kwong or van der Waal, we didn't see k values being part of the equation of state model, right? So that's something. It's a little bit confusing, and that's something also that will be more clear when we will have like by the end of this PowerPoint. But the point is that like when we were discussing k values, we said that the k values are only important, or they have any significance when you have mixture. Here we are only talking about pure components or pure compounds, how equation of state models are applied to pure compounds. And when you have only one component or single component, we know that the k value is always 1. There is no discussion on how the k values should look like as a function of pressure, temperature, and composition, because it's the fixed composition, one molecule splitting into 2 phases. So there is no need for the k values. And equation of state models, when you solve the equation of state model itself, they generally give you this the densities, the equilibrium phase densities, and for pure compound, it also gives you the vapor pressure when we solve for this fugacity constraint. And there is no need for the k values to be known. K values are only needed when we apply these equation of state models to the mixtures, and that's something we will see later on in the slides. So that's something I just wanted to mention here. So now we can go to the exercise, and I hope it will be a bit more interesting than going through all these complicated slides of equation of state models. Okay, so in the exercises, it's yeah, that's 12, and then we have this H2O Excel based EOS. So we just open the Excel file here. Yeah, okay, so in this Excel file, we have 2 spreadsheets. We will be just working on the first one. The second one we will use later when we will finish our next topic. So for in this first spreadsheet, we have Yeah, so what we have here, so that's we are using Suave and Radley-Kwong equation of state model. It was built by Curtis actually, and so we will be using water as a pure compound for these calculation, and these are the component properties that we know for water. We know the molecular weight, we know the TC, we need the PC, we have the PC, and we also have the centric factor, and these are just well known for water. And just forget about this S, what is S and why it's a zero value. So we will not be using this for this particular exercise. And we will come back to that in the next session, what is S actually. So, and then here we have the pressure and temperature. So what we will be doing, we will try to use the SRK equation of state model to calculate the vapor pressure at 100 degrees C, which is the boiling point of the water. And we will see, and we already know that the boiling point at 100 degrees C, since it's the boiling point of the waters, and then the answer should be close to this standard pressure, which is 1.0135 bar. Absolute. And yeah, and these are like these calculations were done in PhaseComp, which is the PVT package we internally use using the SRK equation of state model. And what we have found there, that if we use the SRK equation of state model with and try to find the vapor pressure at 100 degrees C, it gives us 0.9274 bar absolute. And similarly, you can also do the other way around. You can calculate, instead of calculating the pressure at 100 degrees C, we can calculate the temperature at 1.0135 bar, and it should be close to 100. So that's 102 if we calculate that. And so that's the results on the vapor pressure. So these are the results we should expect to get from this spreadsheet. Because these are from PhaseComp or the PVT package. And regarding the densities, so the liquid phase density at this vapor pressure with this SRK equation of state model, that's 0.7104 gram per cc, and we know water density and the liquid phase density at the boiling point for water, it has to be about 1 gram per cc, so close to 1 gram per cc. So you see that there is a big deviation. So if you can just quickly calculate, for example, the deviation, so it's divided by 1, so that's the same. So 30% off. So yeah, and we have already discussed that the densities from the cubic equation of state models, they are highly underpredicted because of the reasons that we discussed before. And the vapor phase density should be very accurate. So that should be okay. So what we are going to do in the exercise, we are gonna do the same calculation, try to come up with the same answers that are shown here coming from the PVT package, and try to apply this Radley-Kwong or SRK equation of state model. So yeah, just to get my life easy, what I will just do is I will just go into the phase behavior monograph, and then just copy the equation so that I have them in front of me while I'm doing the calculation. So where's chapter? So that should be in chapter 4. Yeah. So we know that the Suave SRK equation of state and Radley-Kwong equation of state are essentially the same, and it's only the alpha correction that's different. So we just take the snapshot of the Radley-Kwong equation of state. I hope I'll be able to do that. Please, please, please. Oh. just copy this to the Excel file here. So just to have it in front of me. And then we know that this is the correction term that we want to have in the SRK. Again, no, please. Okay, just leave it. We will just use it from the PDF. Okay, so the first thing, the value of R, and for the unit system we have here, that's mainly SI. So the value of R we can use is 8.31384. So that's the value of R we can use. The omega A value that we can see here, where is that? Yeah, omega A 0.42748. That's our omega A. 0.42748. 0.42748. So that's this number here. Just to make sure I cannot use pen. Oh no. Yeah, so that's this this guy here, and then we have omega B, which is 0.0864, 0.0864. The value of M, so we know that the M is a function of the centric factor, and that equation is here actually in the monograph, 4.17. So that's the M value from the SRK equation of state, so 0.480. Just write it here, equal to 0.480 plus 1.574 times the centric factor, which is here for water, plus, or sorry, minus 0.176 times the centric factor square. Yeah, so that's good. So that's the value of M, and then we can calculate the alpha value from the Suave, which is this number here. A is equal to 1 plus M, that's this number here, times 1 minus square root of the reduced temperature. So the reduced temperature is, we haven't calculated here. We can calculate here that number times the square. Sorry, that is supposed to be a square. And the reduced temperature should be T over Tc. That's the absolute temperature divided by Tc. So 1.539. And we can also, just for the comparison, we can compare it with the Radley-Cohen alpha correction term, and you see that they are quite different. And here, this is just coming from the square root of the reduced temperature, which was constant for all the compounds. Then we have A. So A is this guy here, equation 4.12. A, so omega A times the R square times the critical temperature in Kelvin. R square T square or PC. PC is in bars. That's this number here. Times the alpha correction. This number here. And then we have B, which is omega B times R times DC. So R times critical temperature times over PC, or over the critical pressure. So that's the B value. There is something. So omega B, the B value is where is B? So omega B times R times the critical temperature divided by the critical pressure. Okay, so that's the B. Where is that? Okay, the reduced pressure is P over PC. And then we have the value of A, which is omega A times the reduced pressure. The reduced pressure is this number here, divided by the reduced temperature times the alpha correction term. P over R. No, that's actually correct. That Elena, yeah, that's Elena. That's right. So this has to be 83.134 for the unit system that we are working on. 143. Yeah. Thanks. Yeah. So now we are calculating the value of A. That's simply the value of A here times the pressure, and the pressure is this number here, bar, and then divided by the RT square. So R times the temperature and the whole square. And then we have B, which is B times RT, B times pressure over RT. R times T. Okay. Now we go to, yeah, so we calculate these coefficients here. So the coefficient for this cubic term, that's 1. So that's 1 here, and here it's for the square term it's -1. The A this coefficient here, so that's A minus B. A minus B minus B square. And then the next and the last one is A times B. A times B. Okay. So with these coefficients here, that's the cubic equation of state, and we get these roots. So this is just that's just the code that is taken from this VBA code lifted from this website here, just to solve the cubic equation. So it gives us 3 roots. So there are 3 real roots, and what we are gonna take is we take the root that's the minimum root for the. So we are gonna take this Z1 as the liquid phase root, and then so we discard the middle root, take this one as one root, that's the liquid phase, and then the gas phase is this number here, the vapor phase. And then what we will do, we will try to minimize, because now here you see that there with these we have taken these roots, and with these roots we have calculated the fugacities, the liquid phase and the vapor phase fugacity, and this is the fugacity expression for the SRK, or the quantification of state model. So this is we have calculated, so this is being calculated here, the liquid phase and the vapor phase fugacity. using the liquid phase and the vapor phase root in this equation. And then this is just the difference or the error between the two values, which we try to minimize using the solver, and then try to change the pressure, see which pressure do we get to get the answer. So that will be the vapor pressure when the two vigacities will be will be the same. Try to change this number here by minimizing the number here. That's the error between the two vigacities, and then just try to solve it. Yeah. So we see that it's minimized to exponent minus 24, which is good. And the value we get using the solver is 19274, which is essentially the same as 19274 from PhaseCom at 100 degrees C. So that's the vapor pressure calculated by SRK equation of state model at 100 degrees C for water. And now if you want to calculate the densities, so density now is very simple. We can use the PV equals to NZRT. We know the roots, the Z factors for the liquid and the vapor phase. So we can just take the Z factor times pressure. The pressure sorry, it's the pressure times the molecular weight. Pressure times the molecular weight, which is here, divided by the Z factor calculated. Times the R value times the P value. So this is the in gram per cc, the liquid density, and the same can be done for, I will just fix the formulas and just drag it down for the vapor phase. And if we just compare these two numbers with the numbers we have gotten from PhaseCom, 71024, 71026, and 0.00054, 0.00054. So yeah, so that's how in the equation of state model can be applied to a pure component to do the phase behavior calculation, calculating the vapor pressure and also calculating the densities at vapor pressure by maintaining this viscosity constraint. So I think that this is so any, I don't know if there are any questions on the exercise. Karis, you want to say something?
Yeah, I mean, this shows the mechanics of how an equation of state can be used for a pure compound, or as you'll see later, it's the same exact equations if you have a mixture, and that mixture is single phase. You just calculate an average A, an average B, kind of a molar weighted average. And once you get the average A and average B for the phase, you can calculate its density as well. You can't do the equilibrium calculations in such a simple way, but just the volumetric part, you can do that way. Just an anecdote, kind of an interesting thing about water is that you can get the vapor pressure here exactly at this temperature. And you can introduce the volume shift, which maybe you want to do on your own, or we do it later, so that the liquid density is closer to 1 grams per cc, what it should be. Boiling water has a density of close to 1 gram per cc, right? And what it is now is 0.7.
Yeah.
And so it's 30 It's 29% off. Okay, so if you go look up in your steam tables, density of boiling water, you know, it should be, I don't know exactly what it is, but around 1 gram per cc. It's close to 30% off. And with that volume shift factor up there, the S, you can correct that to be whatever that value should be, 1 or close to 1. Now, even if you do that, the cubic equation of state, if you ask it to calculate the compressibility of water, for example, at 1 atmosphere and 60 Fahrenheit, okay, not at the boiling point, but just tap water coming out of the faucet. That tap water should have a compressibility of, depending on the units, somewhere around 3 times 10 to the minus 6 inverse PSI. The cubic equation, even though it's getting the water density exactly right, let's say 1 gram per cc at 1 atmosphere and 60 Fahrenheit, the compressibility it'll calculate won't be 3 10 to the minus 6. It'll be around 1.3, I think, 10 to the minus 6, which is more than a factor of 2 too low. So the compressibility of water, every petroleum engineer knows, is important, right, in terms of getting water influx correct, well test analysis correct. Getting the water compressibility is a very important property. And you basically can't get it from this cubic equation of state the way it's used now, where we tie the A and B to the critical properties. Now, the critical properties are not of interest, right? 647 K is very, very, very high temperature. We're never going to be close to that. But finding the A and B in this manner, according to
Van der Waals.
Yeah, Van der Waals actually gives 3 ways to do it, but using the PCTC, that's status quo, will give you an equation of state for water. Get the vapor pressure right, can get the density right, tap water or the boiling water, can get all that stuff right. The steam density right will be very close, but it can't give you the compressibility by better than a factor of 2 or worse than a factor of 2. That's something that nobody really talks about, but it's just a fundamental failure of the cubic equation of state. It doesn't have the correct pressure volume temperature relationship everywhere. So it's just kind of an interesting fact. Nobody is computing, not PVT-Sim, nobody's computing water compressibility for you to put in your reservoir simulator or well testing program based on the cubic equation of state, despite the fact that you can get it to predict all these other important water properties accurately. So it's just a kind of a footnote.
And just one comment, Course. Correct me if I'm wrong. So when you're saying that the cubic equation of state model is not predicting the compressibility, right? It means that the cubic equation of state model is not predicting the variation of density with respect to pressure, right? So you can use the volume shift to match one density point exactly, but you may not get this function of density as a function of pressure. Exactly.
That's right. You can get it right at one pressure, but then if you just move over in pressure and want to know the density there, it's going to be way off. It's basically the pressure derivative of this is not being calculated accurately at all.
So this volume shift, what is volume shift? And we will go through this tomorrow and then just do the same exercise in introducing the volume shift. So it will be almost identical, except a very small change that we will see tomorrow when we'll do the same exercise. And let's see how much we have to cover on volume shifts. Yeah, so I think we can, there is a, maybe we can finish the session today now, I guess, because the next topic, if we will start this next topic on the volume shift, it may take some time and we may go over time, which is may not be okay for some of the people here. So, Matthias, do you think it's okay?
Yeah, we have 15 minutes. So
Yeah.
is there any questions in general about some of this? I think from when we've done this course sometimes now, and this is the part that probably many of us might seem as being the most far-fetched from what we do on day-to-day basis. But it's very, very nice if you work on these things, at least seen this stuff at least once, and because that will really help you when we get to the topics tomorrow, which is actually purely on the practical aspects of creating and tuning an equation state model. Hopefully by the end of the week on Friday, we're able to connect the dots going backward a little bit to see the big picture and how this affects the things that we talk more about in a day-to-day setting. Curtis?
Yeah, no, I mean, I think it's, people are tired and it's kind of heavy stuff for us normal engineers. So, I mean, it's, if there's no questions, the only, maybe we'll just ask if there's any questions before stopping. I'll make a couple of comments if there are no questions. I'd rather have the questions come, and if there's any out there regarding the cubic equations of state. I mean, one of them should be, why would you use the Peng-Robinson instead of the SRK?
Yeah. Which US is more preferred? Yeah, that's a more general question we usually get from the.
Maybe, does anybody have any thoughts about that, or are there any like company policies out there for people who use software that you're supposed to use the SRK or the Peng-Robinson, or it's up to you? Any thoughts or comments to that?
I only came across Peng-Robinson my entire career, so it's yeah, but it's just because I'm a follower, so not because I ask the question.
Right.
Okay.
Right.
For me, it's more than. Sometimes it seems that SRK fits better, and sometimes Peng-Robinson fits better.
Yeah, that's very likely everyone's experience if they use both enough. Because the SRK came when it came earlier than the Peng-Robinson, even though it was only a few years earlier, the process industry was, and refining and mainly process industry, really took it to heart and started using it very actively as soon as it came out, because it did such a great job in predicting the accurate processing of gases in particular to extract out liquids and liquid products, and altogether optimizing separator conditions, designing large process facilities like the Ekofisk. And what was available was the SRK and commercial software, the early commercial software. So that became the hat all processing chemical engineers wore up until Peng and Robinson in 76, but then they had to fix the equation in 77, 78 with this quadratic term on the M. And so if you asked anybody in 1978 using equations of state in the process industry, they would say, well, there's no reason to change to the Peng-Robinson. They were all on board with the SRK. That continued through the 80s and probably into the 90s. Then Payne-Robinson, they came along and they gave an equation of state that predicted better densities of oils, but still off by 10 to 20%. Instead of being off 20 to 40%, the SRK would predict stock tank oil densities maybe 20, 30% wrong. Tank oil densities with the Payne-Robinson were off maybe 10 to 15 to 20%. It was better, but it was far from being good enough. And so why do if you ask all petroleum engineers today, or let's say in 1980 and 90 when it really started being used, petroleum engineers, what equation of state do you prefer? They would have said the Payne-Robinson equation of state. And you actually had this kind of war going on between process engineers and reservoir engineers, because reservoir engineers started using compositional reservoir simulation with the US starting in 1980. They didn't use it very much, but the first commercial US reservoir simulator by Keith Coates came in 1980 publication. So in the 1980s, you started doing more and more compositional reservoir simulation, but the EOS being used by the reservoir engineers was boohooed by the process engineers. Didn't have enough components, didn't use the right equation of state. They wanted to have an SRK with more components. So it was like the two groups didn't talk to each other. So the question is, why did the petroleum engineers start using Payne-Robinson instead of the SRK? Well, the reason for that is Robinson came out of the University of Michigan. That's where Katz was, okay? And the first paper on cubic equations of state in the petroleum engineering literature was the Katz and Firzabadi paper in 1978. And there was actually another paper, I think in 77 by Katz and Bergman. Bergman was one of the late PhD students of Katz, University of Michigan. And out of this camaraderie, I suppose, they published Katz and Firzabadi on the Payne-Robinson equation of state. So it was an arbitrary choice in a sense, in terms of, you know, what school do you root for when they're playing football? It was more or less like that. There was no definitive paper that said in 1983 the Payne-Robinson is always better than the SRK. Okay. Certainly not in 1983, because in I think it was 81, the volume shift came in, which we'll talk about tomorrow, I guess, by Peneleu. I think it was 81. And at that point, they made the accuracy of gas and oil densities between the SRK and the Payne-Robinson essentially identical, and within 2-3%. So there was no reason, you know, to choose SRK versus Payne-Robinson. So really, the petroleum engineering industry took the Payne-Robinson simply because the Katz-Firzabadi paper was the first paper they saw. Keith Coates also, who did the 1980 paper on reservoir simulation, used the Payne-Robinson, and he was also a University of Michigan PhD student. So it was a little bit alma mater, if you will, decision for the Payne-Robinson. Whereas for the SRK, it was the first thing available in commercial software in the early 1970s. So that's kind of the background for the two equations of state. Now today, if you go to the process engineering or the chemical engineers doing process engineering with HYSYS, and you ask them, they'll probably say, I don't really care. And one of the reasons for that is because the equation of state work being done for reservoir engineering applications, and probably the vast majority of that being done with PVT-SIM the last 30 years, was accepted by the process industry. In other words, the process engineers didn't have to develop their own equations of state any longer. The PVT-SIM usually gave 22 components, enough detail. Of course, it recommended and only had the SRK in the first 10 years. But then when the Payne-Robinson appeared, likewise for HYSYS, not that HYSYS didn't get the Payne-Robinson until 15 years ago. So, but once the last 15 years, coming out of PVT-SIM or HISIS, the characterization could be randomly Pang-Robinson or SRK, it didn't really matter. So it basically that argument for one being better or preferred over the other died out about 10 years ago. I don't know if there's any questions, but that's kind of the status today. There's never been a singular paper that says this is why you should use the SRK or this is why you should use Pang-Robinson for petroleum systems.
Okay. Yeah, there is a question.
Hi. Yes. There are some scenarios where we have a transition, right? Transition to dense phase. So in that case, which one is the recommended, or which one is better compared to? I think both are equally both SRK and Pang-Robinson will have equal issues with respect to handling dense phase transition, right? So in that case, what would be the advice
for water?
No, not for water. For the hydrocarbon mixture.
Yeah. And the question, could you just repeat it one more time? It was a little bit low.
No. What I was asking is, for example, in a topsides process simulation with using HISIS, whether it is SRK or Pang-Robinson, we have found that both of these struggle when there is a transition to dense phase.
A transition to dense phase.
Yeah. So in that case, HISIS has an option while defining the fluid package to force it either to the liquid phase or to the gas phase by dense phase tuning factor.
Okay, what would you call a dense phase? Is this
above the Krekenden bar? Say.
Okay, yeah.
So in that case, is there any recommendation on the effectiveness of SRK or Pang-Robinson, or which one is better?
No, not at all. I don't think that what I would just call single phase, you're calling the dense phase, basically at high enough pressure, it's single phase. Single phase, high pressure gas or oil won't be predicted better by the SRK or the Pang-Robinson consistently. I don't believe anyone's shown that, and I wouldn't prefer one over the other. When you get to high enough pressures like 7, 8, 900,000 bar, neither of the equations are going to give you compressibilities. Well, even at 600 bar, the compressibility of single phase gas or single phase liquid will not be right. For the same reason it's not right for water. The cubic equation just doesn't have the pressure volume dependency. It's cubic and volume. It needs to be different than cubic and volume to be right, to get the compressibilities right. So any single phase high pressure gas or liquid would suffer from, you might get the right density at initial pressure, but you won't get the right compressibility at the initial pressure.
So in those type of scenarios, then what is the go-by method to ensure that what the simulation results are given are right?
Using a compositional model with an equation of state. Was the question how to make sure?
No. The question was actually, I understood that both will have issues because the predicting the compressibility will not be right. But in this case, what would be the go-by method? What is the recommended method to ensure the simulation results stick?
Yeah. So. The equation of state will never get the compressibility of the high pressure gas or oil right. That means that your recoveries are going to be wrong. The material balance it calculates in your simulator, every grid cell, it'll be wrong, okay? And maybe significantly wrong. You could try to use a black oil model But the problem with that is it's generated from the equation of state now. So the Blackwell tables would have the same poor compressibilities at high pressures because they're generated from the equation of state. So you have a problem with high pressure gas and oil reservoirs in reservoir simulation. There's kind of two approaches to dealing with that. The one is to use a more sophisticated, like a BWR type equation of state to get the compressibilities right, and then generate the Blackwell tables with that equation of state. But there's almost nobody using BWR type equations of state for these mixtures, petroleum mixtures. The other would be to use laboratory data, CCE data in the single phase region up to initial pressure, and to create synthetically or manually the BO or the BG pressure dependence that honors the laboratory measurements of compressibility, which would be correct. So it would be a manually created Blackwell table. If you have to use compositional equation of state modeling and want to get that right, the compressibility of the system and the recovery of the system from high pressure to, let's say, down to saturation pressure, the only way to do that is to correct the total system compressibility, meaning rock, water, and hydrocarbon. Hydrocarbon is going to be wrong. So what you have to do is you have to artificially change the water and or rock compressibility to give the correct total compressibility so that you get out the right amount of fluid as you deplete the pressure. So that's been done in a number of cases in HTHP reservoirs. You have to do this, again, it's a manual exercise to get those water and or rock compressibilities to change as a function of pressure such that the total system compressibility is changing correctly. Those are your three options.
Okay, thank you.
Most people just ignore it and don't know that it's wrong.
Okay, fine. Oh, this is one thing. There is another question. Actually, apart from these SRK and Penge-Robinson models, right? Nowadays, I think there is one more thing which is called the Cubic Plus Association, CPA, which is being introduced by software like Multiflash. I think KBC. I think they have made that CPA as the default model. So, could you also elaborate on the application and usage of the CPA?
Is it being used in a reservoir simulator, you said?
Yeah. So even Multiflash with the one which is by KBC, no? Now with the
Yeah, the Multiflash, but that's not a reservoir simulator. That's more for process simulation. So
they say that CPA is advantageous when handling systems with water, and when we encounter hydrates and we use MEGs to determine the partitioning of hydrate inhibitor between the phases.
Yeah, no, they will help you get partitioning of components into the aqueous phase and from water into the non-aqueous phase correctly and more accurately, but those are not available in reservoir simulators. I think you have some of that in PVT-Sim, and you have some of that in the KBC Multiflash software, but not reservoir simulation. I still haven't seen whether the CPA gets the compressibilities correct. I don't think it does. So for water.
Okay.
Yeah.
So what I understand is, except that partitioning, it doesn't have any other specific advantage. So in that case, is it if polar components are present, is it better to cross-check with CPA only for that specific aspect and do the other simulation in with SRK or Penge-Robinson, or how it will work?
I think there's been a number of publications, and one of which we did back in I think it was the late 80s. Shows that the cubic equation of state can be used very accurately to get component partitioning for aqueous and non-aqueous phases in petroleum applications. you have to use a different mixing rule, but the cubic equation can be used